All right, so let's go back to doing math again. So let's see the structure of ZP and Zn. So the structure of ZP and Zn. So again, like there are some things that doesn't happen in Zn. Like for instance, that doesn't happen in Z. Like there could be two numbers where the product is zero, while the two numbers being non-zero in Zn. That could happen, but that doesn't happen in the real numbers or the integers. So we will look at some things where we get an approximations of the real numbers and the integers. So that is given by the quotation of the following theorem. So we have theorem 2.8. If p is bigger than 1 is an integer, then the following conditions are equivalent. Then the following conditions are equivalent. So what are those conditions? So the first condition is that p is prime. And the second condition is that for any a not equal to 0 in Zp, the equation ax is equal to 1 has a solution in Zp, and the third condition is whenever b times c is equal to 0 in Zp, then b is equal to 0 or c is equal to 0. So let's prove this. So proof of theorem 2.8. So first we prove that 1 implies 2. So suppose that p is prime and a is not equal to 0 in Zp, then in Z, a is not congruent to 0 mod p by theorem 2.3. Hence, you have that p, because it's not congruent to 0, so that means that you have that p does not divide a by the definition of congruences. So now the GCD of A and P is a positive divisor of P so it must either be P or 1 as P is prime, and so must be P or 1 as P is prime, and since the GCD of A and P also divides A, and P does not divide A, so we must have that the GCD between A and P is 1. So by theorem 1.2, the linear combination of A, U, and PV is equal to 1 by Bezout's theorem for some integers U and V. So that means that AU minus 1 is equal to P times minus V. So that means that AU is congruent to 1 mod P, which tells you that therefore that AU is congruent to 1 in ZP by previous theorem, by theorem 2.3, which means that thus A times U is equal to A times U, which is 1. So that X is equal to U is a solution of A times X is equal to the class of 1. Alright. So now let's prove that 2 implies 3. So we'll use, so suppose that A times B is equal to 0 in ZP. So if A is equal to 0, there is nothing to prove. There is nothing to prove. And if the A is not equal to 0, then by 2 there exists there exists U in ZP such that AU is equal to 1. So therefore zero is equal to U times 0, which is U times A times B, which is U times A times B, which is A times U times B, which is 1 times B, which is B. And in every case, in both cases, so in both cases, you have that A is equal to 0 or B is equal to 0. So now let's show that 3 implies 1. So suppose that B and C are any integers, and we have the following, and P divides B times C, then B times C is congruent to 0 mod P. So by theorem 2.3, B times C is equal to B times C, which is 0 in ZP. So hence by 3, we have, no, hence by 3 there is no we have, we write B is equal to 0 or C is equal to 0. Therefore B is congruent to 0 mod P, or C is congruent to 0 mod P by theorem 2.3. So therefore P divides B, or P divides C by definition, and therefore by one of the theorems earlier, P is prime. And we're done. So yeah, I hope you guys enjoyed this video, and we'll continue with this subsection next time. Bye now.